Hey guys, welcome back. This is Frank, and welcome to our IGCSE CoSci Physics revision videos. Our current unit is P4, Light and EM Spectrum. So let's start off by considering this scenario. We have a plane mirror. Well, we know that a plane mirror is just another name for a flat mirror. So it's flat on the surface, it's not curved, not inwards, not outwards, just flat. And we also know that there's a habitable light ray, and we know that it's coming from this direction to this direction. So, from coming from here to here, it's shooting straight towards the plane mirror, and we know that by the arrow on the light ray. So don't forget to draw your arrows. And we know that the angle of incidence, we write theta I to represent angle of incidence, is 55 degrees. Now, they're asking you to first complete this ray diagram, and second, find out the angle of reflection. All right. So, where do we start? Well, pretty much for any question, we always start with drawing a normal. So I've already drawn a normal here, as you can see. And be reminded that a normal is just a line that is perpendicular to the surface of the plane mirror, and it's drawn at the point where the ray touches the mirror, and this is a normal. And we also know by definition that the angle of incidence is the angle between the normal and the incidence ray. So we know that this angle is going to be our angle of incidence, or theta I. So that's 55 degrees. So it's asking for us to complete the ray diagram. So as because we are very smart people, and we know that this is a very important rule that you have to remember. We know that the angle of incidence is equal to the angle of reflection, and I'm gonna just give it a box outside and put some stars and put it in red, because that's very important. And why is that important? Because it's on the syllabus itself. So you must know this. You must know that the angle of incidence is equal to the angle of reflection. And that's something you have to remember. Well, we kind of already solved the second problem because we know that the angle of incidence is 55 degrees, so the angle of reflection has to be 55 degrees as well. But let's suppose we don't know that, okay? And we're going to find out later. So, we're going to draw this ray diagram, and we know that theta r is going to be 55 degrees, unsurprisingly. And by definition, we know that theta r is also the angle between the normal and the reflected ray. So we know that the angle between the normal and the reflected ray, somewhere over here, is going to be 55 degrees. So conveniently, we take out our ruler and protractor, and oh, nice. So we know that. And we know that that's going to be 55 degrees because I sort of measured it. But anyway, we're just going to put over here and draw a pretty line. And we're going to always don't forget your arrows. And we know that's going to be the angle of reflection, which is also 55 degrees. So we sort of answer this question. It's 55 degrees. All right. So what is the takeaway from this from this little problem? We know that angle of incidence is equal to angle of reflection, or theta I equals to theta r, and you have to remember that. Draw some stars beside it. Circle it, box it, whatever you want. But make sure that you memorize that on the test. It's pretty easy because apparently, it's not very hard math. It's just an equal sign. Anyway, so moving on, next we would like to know some of the properties of images formed by plane mirror. So think of what you see on the mirror. If you stand in front of a mirror and you see, of course, a reflection of yourself. So how is that image? How can we describe that image? So we know that this image has some very interesting properties. So first of all, it's same size. All right, and we are talking about plane mirror here. So if your mirror at home is a little bit curved, maybe you'll see yourself like fatter or whatever. But in a ideal plane mirror, it's gonna be the same size. And the next property is that they are the same distance from the mirror. So by same distance, it means the distance of you from the mirror and the distance of the image from the mirror is the same. So let's say you are a happy little person standing here, and this is a mirror, and then you see yourself, another happy little person standing here. Oops, that's not very imagey. Maybe more like that. Yeah, okay. And you know that the distance between you and the mirror and the distance between the mirror and your image is gonna be the same. So these two are gonna be the same. So that's what it means by same distance. Uh, Another thing you'll notice is that it's upright. So, well, apparently, because you're not gonna get an upside down image like this, which is gonna be really scary, by the way. So, we know it's upright, and we also know that it's a bit hard, but it's called laterally inverted. Oops, I just spelled laterally wrong. Laterally inverted. That's two words, so inverted. Okay. So what do you mean by laterally inverted? Think of it like this. So let's say you have a letter D in front of a mirror. What is it gonna look like? Well, you know that it's gonna be upright, so it's not gonna be upside down. But you know that it's gonna look something like this. Try yourself. Write a D, big D on your paper or something, and hold it in front of a mirror, and you're gonna look something like this. So it's left to right inverted. So that's basically what we mean by laterally inverted. It's just left to right, left to right. Okay, and the last but also a very important characteristic is that this image is virtual. Now, this is a very important concept because you need to know the difference between a virtual image and a real image. So virtual, aka not real, well, apparently. But what does it mean, a virtual image? Think of it like this. So a virtual image cannot be projected on the screen. That means it's made up of virtual rays instead of real rays. So there aren't actually any light rays behind that mirror. It's just you seeing yourself. It's just light rays reflected instead of like actual light rays passing the mirror. So it cannot be projected on the screen. And later on, when we move to converging lenses, you'll see that converging lenses most of the times form a real image, which we can see on the screen. Anyway, so here are 5 of the most important features of a plane mirror: same size, same distance, upright, laterally inverted, and virtual. So cannot be projected on the screen. All right, moving on. We have something very interesting. So in paper 6, or what we call alternative to practical, you might get these kind of questions. So you might get an experiment that asks you to measure a light ray reflected by the mirror, and it's asking you what are the possible causes of the error, and uh, something that you can do to make this experiment more accurate. So what are some of the causes for this error? Well, considering what we did over here, some causes of this causes of error for this experiment might be, let's say, first of all, the thickness of the mirror. So we know that only under a very ideal mathematical situation would the mirror actually be a straight line. But in real life, mirror have width, so you might get a mirror that looks something like this, and then it probably has a little stand behind it. But anyway, it's gonna have thickness, so you can't exactly tell whether the mirror is exactly on this line when you place it in a practical. So the thickness of mirror might be one of the causes of error. And another thing is the light beams themselves. So thickness of light rays, or you can say light beams. So what this means is that, the light beams, if you're using a ray box, let's say, the light beams coming out of that ray box also has a thickness, so you can't quite tell where is the middle of that light ray. So your measurement might be a little bit off. And another very important thing to consider is the accuracy of your protractor itself. So let's say protractor, usually the protractor we use in class can only measure plus or minus 1 degree. So if you look at your protractor right now, it can only show a difference of at most 1 degree. It cannot tell you to the very exact, let's say like 0.1 or 0.01 degrees. So that can also be a cause of error. So you might get like 28 or 29, but you can't quite tell if it's 28.45 or if it's 28.65. Anyway, so here are some of the most common causes of error for this experiment, this Raybox reflection experiment. And yeah, that's pretty much it for the reflection part. So just remember, angle of incidence equals angle of reflection. Same size, same distance, upright, laterally inverted, and virtual are the 5 characteristics of plane mirror. And the causes of error for this experiment might be thickness of mirror, thickness of light rays and or light beams, and protractor can only measure up to plus or minus 1 degree.